So in topic 2.2, motions of charged particle in electrical field, what we're going to determine is not just the field strength, which is a vector quantity of what's the potential energy around the charged particle. We're actually going to start looking at how this converts to other electrical quantities that we know, such as work, such as charge, and such as we can also look at what the motion will be like um, inside an electrical field. So you're going to need to refer to electrical circuits from year 11, as well as a one-dimensional motion from the previous topic. Okay, so we're going to go back to the definition that electrical field give you some form of potential energy. So an example that we went through before include if you got parallel plates. Okay, so you got parallel plates where one side is strongly positive and the other side is strongly negative. Well, it doesn't have to be. Just one side is positive, the other one's negative. And what we find is that the field line in that case, which is imagine a small positive unit charge, one unit, and it's going to move in that direction, vertical, perpendicular to the two plates. Sorry, my drawing is not perfect. Okay, so a charged particle in this context, okay, in this case, it's actually a couple of things is happening. One, it's actually gaining energy. In particular, kinetic energy. Okay, so that shouldn't come at any surprise because um, at similar to gravity, so as a ball dropping down, you're gaining kinetic energy. You used to have potential energy, now you have kinetic energy. And while imagine this being a this also being a free fall, you're also accelerating. Okay, so what you have is you're gonna have uniform acceleration. So let's relate all this to what we know. So first of all, we're going to refer to work done compared to charges and electrical potential. So recall this relation here. Work done, which is a measure of energy, is equals to the change in potential or the potential difference between the two plates, okay, times by the charge Q. Okay, so in effect, what potential difference is what potential difference is how much energy gonna get per charge over the same amount of potential difference. Okay, so normally we express this as Q times by delta V, but in our context, we're going to do a little bit differently, and because we're going to do some deriving. Okay, so that's what we know. And I'm going to, from this expression here, we also know that your work done equals to force times by the distance. Okay, and I'm going to amend this a little bit by saying I want F times by D, where D is the distance between the two plates. So we're assuming that a positive charge is going to start from one end, moving all the way to the other end. Okay, so that's the distance I need to travel. So if a constant force has been applied, then we know that you have, if a constant force is being applied, then the work done is the distance times by that force. Okay? But if your field is actually changing, then that's not going to be linear anymore. Okay, so if I write the two equations together, okay, if I call that 2, oh, if I call that 2, and I call that 1, then by putting the two together, I'm going to get delta V, which is my electrical potential, equals to my force times my distance divided by charge Q. Okay. Now, finally, we also recall that F from the previous chapter, F equals to Q which is my charge, times it by my electrical field. So which means this equation here now becomes delta V equals to charge E and so charge Q times by electrical field. And hang on, let me rewind a little bit. Okay, so let me rearrange this one first. So I've got, if I have F divided by Q equals to my electrical field E, okay, then what we're going to end up, which is really this part here. So what I'm going to end up with is I'm going to have delta V delta V equals to electrical field E, which is like a rate of energy gain, times it by distance D. Okay, so we found another, this is another expression for electrical field. Another expression for electrical field is E equals to delta V divided by D. Okay, now let's actually dissect this a little bit further. So we're saying that bring back my parallel plates. So electrical field strength E is dependent on how far apart the two plates are. Okay? So if I have the same potential, okay, I have the same charge on either side, or one is certain amount of positive, certain amount of negative on two sides. By increasing the distance, I'm actually weakening the electrical field strength. Okay? By increasing the distance, I'm going to decrease my electrical field strength. So, and bring back to understanding that electrical field strength is a potential.